We'll be starting at 6:40, so please call your friends and batchmates. Hello everyone, welcome to K.R.A.I.G 301 organized by Technology Robotix Society. So let's try to dive into the world of image processing. Ayush, next slide. So what is image processing? So there's a slider link which is being put on the chat box. You could answer what do you think about image processing. Everyone do try answering. It's not necessary that it has to be correct or something. Just try answering what's your perspective or what do you think about image processing. All right, so we have gotten a lot of answers. So let's start with the basics. Ayush, can you move to the slide? Right, so we have gotten, okay, image processing is operation on images, analyzing images. It's about computer vision, processing images, reading images by computer. Right. M- A lot of the answers are correct. So, okay, let's start and let's actually try to find out what image processing is all about. Right. So first of all, let's try to think. How do we see an object? So light falls on our eyes and we see the details of the objects, such as its color, shape, and size. After getting all the information, our brain tries to understand the image. So it is clear that the image has to be well fed in our brains for further processing. Similarly, in computers as well, we need to get the image through the camera and get it stored in a computer understandable format, like binary digits. After getting the image stored in the computer understandable format, then we can operate on that and do some image processing tasks. So image processing is concerned with performing some transformations on an image, such as smoothing, sharpening, contrasting, stretching, etc., on the image for making it more enhanced and readable. The input and output of this process are generally images, but there are also cases when we receive output as graphs, for example, in image histograms. Next slide. All right, so now what is computer vision? So whenever we think about image processing, we always talk about computer vision. So to perform any of the image processing operations such as stretching, sharpening, brightening, we need to write the code and process the data obtained from the image, and that's exactly what we do in computer vision. So the goal of computer vision is to write a program that can interpret images. So computer vision has various applications such as in robotics, surveillance, healthcare, and building 3D representations. The most recent example is in self-driving cars. So self-driving cars have a lot of coding related to machine learning, deep learning. But before all that, the most basic thing that we need is to feed it with images on which we can apply all these operations. Next slide. Right. So matrix representation of an image. So we know that we need to get the image in a format which is readable by the computer, right? So matrix, so we represent the image in the form of a matrix. So a matrix is a 2D grid where each coordinate will represent something. So we can think of an image as a function. Next slide. So an image is a function and it's represented as a 2D grid where x comma y can represent some property such as the intensity. A color image is just three functions pasted together and can be written as a vector valued function. So the color image is the three functions of RGB, which is red, green, and blue. And all the colors that we know can be represented as a combination of these three functions. Now, images as functions. So on the top left, we have an original image of the Terminator. The top right is the same image in a 2D format, whereas the bottom two are in a 3D format. Now we can see that this particular image is on grayscale. So let's try to look at what color scales exactly are. So there are various color scales such as grayscale, RGB, HSV, and Y-CBCR, out of which the first three are more common. So let's try to look at all of them in depth. So grayscale. Grayscale is the amount of grayness or shades of gray at a particular point in image. So the top left image we can see is a black and white picture, whereas on the top right it's a 2D representation of the image. So on the right hand side we see that some of the grids or pixels they are black, whereas a few are white and the others are a shade between the both of two. So the black ones have a are represented by a number 0, whereas the white ones by the number 255, and all the others lie between both of these numbers. The bottom image is the same image converted into a 2D format, and it's you can see that it's quite pixelated. It has got a lot of dots, so there are values that have been stored in the 2D image. 2D image is not a continuous image. Like it has only a particular value at a particular point. Um, I used at the previous slide, Peter. Right. So there are a lot of details which are represented by dots and colors such as white, black, and the shades in the middle. And we can see that this leads to a lot of loss of details. Like let's try to understand this in depth. Next slide. Right. So on the left hand side, we have an original image of Barack Obama, whereas on the right hand side, it's the 2D map of the same image. So we can see a lot of boxes on the right hand side, which are the pixels. But in this image, we notice that a lot of details have been lost. So if you want to have the smallest details, you will have to increase the number of pixels. Like the most common example or relatable thing about this is the YouTube videos where the quality ranges from 144p to 1080p. 1080p, you have a lot of crisp and clear image because there are a lot more pixels which are packed inside and the smallest details are stored. Whereas in 144p, we have less number of pixels and hence less data. Next slide. The next scale we are going to look at is RGB, red, green, blue. And I think most of you are pretty familiar with it. Like a lot of gaming laptops have RGB keyboards and they look pretty cool. So RGB, as previously mentioned, we can it can be used to represent each and every color that we know. On the extreme left, we can see that there's a picture of the groceries. Then we have three mappings. In the R case, it represents the amount of red present on that point in the image. So the places that have a greater intensity of the red color are shown by a brighter red, whereas those with a lesser intensity have a deeper color of red. When the same image is converted to grayscale, the places that are represented by a deeper color of red get converted to the color black, whereas those with a brighter red are closer to white and its corresponding shades. Similarly, it's for green and blue as well. Alright, next slide. So HSV, that is hue saturation value. Let's try to understand this word by word. So first of all, what is hue? So it is the primary color, red, blue or yellow, and the secondary colors obtained by mixing them, which is orange, green and violet. Basically, these are the colors that we see in a rainbow or a color wheel. Now, what is saturation? It is the purity and density of the color. So the ones with a higher saturation have more vivid and intense colors, whereas the ones with a lower saturation are closer to pure gray on a grayscale. The value is the relative brightness of the color. We know that the RGB scale is represented from 0 to 255, whereas grayscale from 0, whereas the grayscale is also represented from 0 to 255. For HSV, we have the hue being represented by degrees from 0 to 360. The saturation goes from 0 to 1 and is distance from the center axis, which can be seen on the image in the top right. The value is distance along the strand length from the top. Now we already have grayscale and RGB scale. So why do we need another scale? Why do you think HSV scale is also very important? So this is because even if the brightness changes, the actual color does not get lost, like the details of the image remain. So on the top left, we can see that there are two bots, red and blue. And let's say the blue bot has to hit the blue colored core, whereas the red one has to hit the red colored core. Now what if you decrease the brightness? So there are chances that the blue bot goes and hits the red one, whereas the red goes and hits the blue colored core, and that would be really disastrous. So over here, HSV comes to rescue. So the HSV focuses on the real color or the hue of the object. So now that we know about color scales, let's move ahead. Alright, so what is a digital image? So we usually operate on digital or discrete images. A digital image is basically a computer understandable image. So it maps the sample onto a regular grid and it quantizes each sample, that is rounds it off to the nearest integer. The image is now represented as a matrix of integer values. So now let's look at an example of the matrix representation. So over here we can see that every grid is assigned values from 0 to 255. 0 represents the black color and 255 the white color. The numbers which are close to 0 represent the darker shades or the shades which are almost close to black and, and vice versa. All the other numbers represent the shades of gray or the colors between obtained by mixing black and white. Alright, so let's move to the next slide. So now what is sampling and quantization? So sampling is a basic operation on the operation performed on digital images. So in this process, the continuous time analog signal is sampled by measuring its amplitude at discrete instants. And over here, it is necessary to choose the sampling rate properly, so the sequence of samples uniquely defines the original image. And what is quantization? So quantization is the sample values to a finite number of levels, and each value can be represented by a string of bits. So to quantize a sample value is to round it off to its nearest point among a finite set of permissible values. So let's try to understand this deeply. So on the left hand side, we see that there is an image, and on the right hand side is the 2D representation of the same image. But we notice that the shape is not the same in both the scenarios. Why is this? So on the left hand side, when the shape of the object of whichever occupies the area of the grid greater than 50% has been covers the entire grid on the right hand side. Whereas if it occupies less than 50%, it is not represented at all, or the entire grid is left blank on the output image. We also notice that we have obtained discrete colors on the right and the colors do not match exactly to the ones on the left. So why is this? So this is because we have on the left hand side a particular range of colors is is mapped onto a particular color on the right hand side. So a particular range of colors, let's say from some number to another different number, gets mapped only onto a single color on the output image. Alright, so let's move ahead. Alright, so now that we know about digital images and we have obtained it, so let's try to understand what image processing is actually. So image processing operation typically defines a new image G in terms of an existing image F. So we majorly have two operations. One is on the range of F. So what happens over here is that the values that we are going to put in the final 2D matrix is based on what we have in the original image. The second mapping is on the domain of F where we change the orientation of the image. Now let's move ahead and let's look at a teaser. Alright, so why is RGB not used all the time? So the slider link has been put in the chat box. Everyone try to answer it. So we have gotten quite a few answers. Let's look at the Right, so most of you have answered correctly. This RGB consumes more memory. So let's try to understand this. Can we move on to the slide? Right, so the reason why we not use RGB always is because grayscale ensures optimum utilization of memory. So RGB consumes more memory. The reason is that a total of 3 into 256 slots, since it has values from 0 to 255. Whereas on a grayscale, we will only need 256 slots, and it's not always necessary that we need to know all the details. Like for example, for edge detection, it's not necessary that you have to know all the details. So hence we do not use RGB all the time, and since a lot of memory is consumed. So let's move ahead. So now we know the basics of image processing and about matrix representation. So now let's try to understand what image arithmetic is. Nikhil would be moving ahead with this now.
Yeah, thank you, Tanushree. So, hello everyone. So, as a recap, what we just learned is that images are represented as numbers internally and computationally. All right. So, when we are working with image, we receive a series of numbers, a matrix of numbers, and then, as the name suggests, we want to process it. We want to work with it. So the first thing which comes to mind with these numbers is maths, to apply mathematics and statistics. So I know a lot of you doesn't like maths. So we'll start with something basic like arithmetic. When I say image arithmetics, what I mean is applying something basic operators such as addition, subtraction, multiplication, or division on these images, on the various values which represent the images, or you can say the pixel values. Though by definition it might seem something very basic, something which is just for teaching purposes, but in actuality it is used even in one of the most complex projects. Every complex projects have these type of small image arithmetics here and there. So let's look at them. So let's start by arithmetics on an image by a constant. So let's say I want to add something to an image. So here we have the Lina image. Lina image is one of the most famous template used for teaching image processing. As you know, it has everything. There are bright spots, dark spots, and lot of details. So let's say I add every pixel by a value of 50. This means that a pixel which has a value of 10 will become 60. A pixel having a value of 150 will become 200. A pixel having a value of 250 will become 255. Because as Tanushree earlier mentioned, that a value of a pixel in a grayscale image can be either 0 and 225 between them. It cannot exceed 255 or it cannot go below 0. So if a value of pixel becomes, let's say, 300 in our case, the computer will tourniquet it and say, okay, it's 255. If it becomes 0, become below 0, then it would be considered as 0. Okay, so what happened is the value of the pixels shifted from the original position towards higher values, towards the white side. So we can see as a result, the whiteness of the image has increased. Similarly, when I add by bigger numbers such as 90 or 130, you can see more and more bunch of pixels are becoming white. I'm seeing those white spots. We are losing details and we can no longer differentiate between a lot of small stuff, right? And a lot of you who have worked with image processing applications know that increasing this kind of whiteness is referred to increasing brightness of image. So when you add an image by a constant, the value shift towards the 255 side, leading increase in brightness. Similarly, you can think that if you subtract from an image, let's say I have the Lena image and I'm subtracting it by 20. So what would happen is a pixel having a value of 50 will become 30. A pixel having value of 10 will become 0 because again it can't go below 0. And the brightness of the image, the whiteness of the image will decrease and you will start seeing the black spots appearing on the image. Now, this was a simple operation where we had an image and we added or did arithmetic operation using constants. But we can also use two images, arithmetic operation between two different images. So let's see subtraction in this case. So what happens is we have an image one and image two. So when I say we'll subtract these two images, what I mean is the let's say the top left pixel of image 1 will be subtracted by the top left pixel of image 2 and the value will be the new answer, the result, the top left pixel of the result of this subtraction. In the first example we have our original image, the one we want to work on, and image 2 here is a binary image and a bit special image, as such type of binary images are called mask. Why is it called a mask? The image 2 consists of white pixels. It consists of fully white pixels, 255 values, except a shape of our choosing. Here we have a star shape. So when I subtract it, think about it. Every pixel in image 1 has a value between 0 and 255. When I subtract it from a 255 valued pixel, it will either become 0 or it will be below 0. And as I said, if it goes below 0, it is assumed to be 0. So every part in image 2, which is white, will result to a black part in our result image. And since a black resembles a value of 0, subtraction by 0 means nothing. So the part inside our shape, the part inside the star remains the same. And though this might seem a bit useless or not that useful method, it is really useful. Let's say you are having a bot which is looking for stop sign or go signs every second. What it will do, it will take a picture, analyze the picture. Do I have to stop or do I have to go? It will find the sign in the entire picture and then go ahead. But if the bot knows that the sign is going to come in the right hand side of its field of vision, then what it can do is it can mask the entire image, throw away the useless left part of it, and just focus where it expects the sign to come. Using this, using this small process, you can save a lot of computational process, and your bot can do its operations really quickly. The second example here we have. So let's say you clicked a photo, and a few minutes later, an object came in your field of view, and you again click the photo. Now, during this time frame, a lot of objects in your background will remain the same, and the object is the only one which entered your field of view. So when you subtract these two, like here we see the current frame and the background model. When you subtract it, a lot of the objects will remain the same. A lot of pixel holds the same value. Practically speaking, due to change in lighting and stuff, your pixel values can differ by one value, two or three, let's say 10, but it won't differ more than 10. So when you subtract them, the result will be every same objects would get cancelled out. But the only part where the object entered will have abnormal value, let's say 200, let's say 100. Okay, it won't be very small. And if we do a process in the thresholding, because as I said, the same parts will have less than 10 difference, and the part which just entered our frame of view will have a bigger difference. If we threshold and say, okay, every pixel having value 10 or less than 10 should become 0, and every pixel having a value greater than 10 should become white. So you receive this binary picture where the object you want to track or the object you want to look into is separated out. And even this can be used in a very unique ways, such as you can make a crude motion sensor. You can take a picture, compare it with the picture you took in the previous second, and compare the objects which move. And if something moves, then you can sound the alarm for the motion sensor. As simple as that. Another special case of subtraction will be making negatives of an image. So we know that subtraction is an order process. Like image one and image two are in this order. That's why the result is this. If you change the order, then the result becomes different. So when we want negative of an image, let's say our target image is at the second position, and our first image is a plain white. All the pixels are 255. Now, I know most of us have never seen a negative since we were born in digital camera age. But what negative basically means is that the brightest spot in our original image will become the darkest spot in our negative image, and vice versa. So how does subtracting our image from a 255 plane image helps? Think about it. Our plane image has a value of 255. Let's say in our original image we have a value of 200, a white spot. When you subtract it, the value will be 55, a relatively smaller value, darker value. Let's say in our original image, there is a pixel having value of 10. So when you subtract it from 255, it will result into a higher value, 245, a white spot. So using this method, we can turn original images into their negatives, and it is highly useful. Here in the first example, this is a biomedical image. This is a tumor, and where we wanted to observe the nerves. So due to the black background, it is a bit tough to observe the tiny details. But if we take the negative of the image, now the background is brighter and we can see each tiny nerve very easily. Similarly, in the second image, the brightest spot in our original image is now the darkest in the negative. And the crevices between the sphere is now clearly visible since we took a negative. Let's say you want to see if there is some object between those crevices in the spheres. So now you can see it really clearly in the negative image. Moving on, in the previous slide, we talked about something known as thresholding. So thresholding basically helps us to separate objects from other objects or from background. Let's take an example. Let's say we have a black background and in front of it there is a bottle, any color, and it's grayscale, right? So I know since the background is black and the bottle is grayscale, let's say if it was red in color. So I can say, okay, let's threshold the image with the pixel value of 50. So every pixel having a value below 50 would be termed as black, 0, or okay. And every values with the pixel value greater than 50 will be termed as white, 255. Okay, using this, now what will happen is my object of focus, the bottle, will be separated from the background. Now I can track it, I can measure it, and I can even study it. In the given example, we had an image of a cloud, we grayscaled it, then we performed a binary thresholding of value 173. What does this mean? Binary thresholding of value 173 basically means that every pixel having value equal to or less than 173 was termed as black, and every value greater than 173 was termed as white. So now in our grayscale image, we had this clouds mixing with the sky. But now due to thresholding, we have a clear view. Where is cloud and where is clear sky? We have separated them. Thus, binary thresholding helps us in our image processing and in lot of different complicated projects as well. Binary thresholding is also used in text recognition, where the background is white and you are writing with a darker pen color. So you can identify the text using binary thresholding. Now, all this theoretical knowledge which Tanushri and I discussed might, be understandable to few of you, but some of you might still be confused. So let's see practically, let's play with these images and learn how these processes can really help us working with computer vision tasks. So I would like to call Ayush and he would give a demonstration to you. So over to you, Ayush.
Yeah, thank you, Nikhil. So everyone would have got a link for the collab, Google Collab notebook. I would like everyone to open it and I'll give a quick tutorial of what was already mentioned in the mail. So you have to go to File, go to this Save a Copy in Drive, click on it. It will be creating a copy for you. Also, once it is complete, you will get a like you will open it in another tab. So basically, I'll not be using this one. I'll be using the original one. So let's start. Okay, so first of all, we'll be importing, downloading the images. So these are the commands for downloading images. You don't have to like go through the codes right now. Now we'll be seeing, we'll be having the paths of different, we'll be naming the paths of different images that we downloaded over here. So that is what we are doing. Now we'll be importing the libraries that the Python libraries that we require for the session today. So these are basically CV2, Matplotlib, and NumPy. Now we will read the image, and this is the first Lena image that we are using. It is a very famous image in computer vision community. Now we'll be uh, showing the grayscale of the image that we downloaded and showed here, the grayscale version for it. Now for this grayscale version, now we are printing the different values of basically it has been stored in a um, digital image format. So each pixel will have a value for from 0 to 255. So you can see the top right corner over here, it has 144. So, and the bottom right corner, it has 89. So you can see there's a difference in the values. This is more closer to 0 and this is more closer to 255. I mean, this is more gray and this is more towards the black side. So that is what we can see here. It is more on the black side, it is more on the white side. Now we are checking out the dimensions for the array. So it is 512 by 512. That is what we can see, 512 by 512 approx. Now, yeah, so as Tanushri talked about the different color scales, so now we'll be seeing what the different color scales are. So first of all, this is the normal RGB color scale. This line BGR to RGB, basically what it means is when this library reads those images, it reads them in blue, green, red format, but we want them in red, green, blue format. Basically, BGR is blue, green, red, and RGB is red, green, blue, which we are familiar with. So that is what we are doing. So this is what the RGB format is. Now the grayscale version for it. This is the grayscale version for it. Now, Tanushri also talked about the HSV format, the hue saturation value. Now, this is the actual HSV format. When we print this RGB into HSV format, then this is that image. Now we are moving on towards the different color channels that exist. So basically, in the theory, you learned that the values range from 0 to 255. So that is one method of representing the values in integer format. There is another method as well. So in this method, what you do is you keep 0 as 0, 255 is scaled down to 1, and every integer between 0 to 255, that is scaled to some decimal value between 0 and 1. So that is what is showed here. Now you don't need to go through all this code right now. Basically, so this is the original image. Now when we print the red channel for it, basically the all the red intensity is present in this image. So the white the white value, it has all three colors, red, green, and blue. Therefore all three are present with almost equal intensities for the white regions, for these patches as well, these cubes as well. All three will have those. But when we come to red, only red will be present, only red channel is present, the green channel is missing, like here as well. Similarly, when we come to orange, so it will be having a red channel and darker shade of green channel, but there will be no blue channel present because this orange does not require blue to be present. Similarly, blue will only contain blue and not green or red, and similarly for green. Now we'll be moving to the part that Nikhil talked about, image arithmetic. So run this piece of code. Yeah. So what we are doing here is we are taking two images and we are resizing we are cropping one image to bring it to the size of another image, and then we are adding both of them. You don't need to worry about the code for now. We are just all the pixel values of image 1 will be added with all the pixel values of image 2. That is what is happening here. And these thresholds, these values, you don't need to worry about them right now. You can experiment them and put them something between 0 and 1 here, 0 and 1 here, and some value here to see how they get added, how the two images get added. Again, just yeah. So now we'll be seeing subtraction. So when we do subtraction, we are subtracting this image from the Lena image. So the white part, yeah. So this white part, it will have the all the values will be 255. So uh, if I subtract 255 from anything, it will always result in a black image, so in a black pixel. So that is what is shown here. Similarly, this was a white region, and since I subtracted it, so this resulted in black. And other pixel values are like that way as well. They are scaled, those are that values after subtraction. So now if we want to see the negative, so this is the negative of the Lena image. Basically, it is just each pixel has been subtracted from 255 for all the three scales, for all the three channels RGB. So you can run it and see if it is not, if the output is not already present in your system. So now we want to see the negative of a grayscale image. So when we run this piece of code, so this was the original grayscale image of the Rubik's cube, and when its negative is produced, the white will become black. Similarly, the lighter gray here will become the darker gray. The darker gray will become the lighter gray, and similarly for other colors as well, other shades of gray as well. Now we want to see how adding constant values to pixels work. So yeah, so there are several ways of doing this. This is one way in which what happens is, if it reach if the value is 255 for this area and I am adding something to it, then instead of remaining at 255, it will go back to 0 and start from 0. Basically what it means is, the pixel values loop from 0 to 255. That is, if you add something at 255 value, let's say I added 40, so that will result in a 40 value. So that is what is happening here. Basically this was 255, I added a 40 value to it, this pixel, it resulted in a 40 valued pixel. Now this is very dark, it is almost black. Now if I added 80, so this 255, after I added 80, it will become 255 plus 80, it will result in 80. Similarly, this will result in 120. And for other colors as well, this black, it will move towards the lighter shade. So this black will result in a little less black, then again it will go to more on the gray side, then more on the lightish gray side, similarly for other colors. Now what we are doing is, we have these three images with different constant values added to them. Now we are plotting the frequency of different intensities. So in the first image, original image, the maximum intensity should be of 255, right? Most of the image is white. So Maximum intensity is around 255. Now once we added 40, most of the intensity is around 40. So that is what is happening here. Most of the intensity is at 40. Similarly, for 80 and 120 as well. 80 and 120. That is what is happening. Okay, so now that we are complete with the image arithmetic part, I would like Nikhil to take over and get over with the next part. Yes, Nikhil, over to you.
Yeah, thank you, Ayush.
Just
Yeah, all right. So I hope a lot of you got the feel of how image processing works. So after image arithmetics, you would have observed that every processes we did, we were working with single pixel. When I am making an arithmetic process, let's say addition, so I'm adding a value to a single pixel. But in reality, pixel does have the uniqueness, but not in the way we just used it. Let's take our example where we had a black background and a bottle in front of it. Let's say if we take a pixel in the background, the pixel let the value be 2, then the pixel next to it would also be 2, 3, or something nearby, since they are part of the same object. They are related to each other. If you take a pixel at the bottle, let's say the value be 60, so the pixel next to it will be 60, or might be even 61 or 59, but they are related. So pixels are more or less related to each other, and they don't have that much of individuality. So to do that, so that our result is not dependent on uniqueness of every pixel, but when we observe a pixel, we also observe its neighborhood. We use something known as image filtering. So image filtering is basically application of lot of algorithms such that the value of a pixel is also affected by the neighborhood pixels. This method helps us to enhance the image and do a lot of different interesting processes. So let's start by first learning about mask. We discussed a bit about mask, but now let's go to a formal definition. Here we have an input image of a house. If we take that input image and pass it through a transforming function, let's say h, we get an image with brightness increased. We were just doing that. We just added some constant. When the same image is passed through another transforming function h, the image gets stretched. So from here, we can understand that it is not the input image which is governing the output here. The output is governed by the transforming function. Changing the transforming function gives us different types of image. So let's see how it works. How does a transforming function transforms the image? So let's go forward, and we have a video for you. Okay, all right. So here in this video, what you need to observe is this sliding function. Okay, so there is this 3 by 3 matrix. Let's just, instead of the three layers, let's just look at the first layer, the first 7 by times 7 times matrix. Okay, now that matrix is constantly being multiplied by another matrix, the 101, 110, 11 minus 1, 3 by 3 matrix. That 3 by 3 matrix is basically taking the dot product each time and giving a resultant value, and it is doing by sliding through the image as it was shown in the video. So first it will start with the top left corner, take a dot product, update the top left pixel in the resultant image, then move a step ahead and take a dot product, update the value in the resultant image in the next pixel, move a step forward, and doing that it would slide through the entire image and start taking dot products. How does taking dot product help us? We'll come to that a bit later. But right now, what we are doing is this is a function, how a transforming function uses the neighborhood of a pixel. Here, when we are taking the output, we are not just considering a single image. Here, we are taking a 3 by 3 kernel. We can also take a 5 by 5 or 7 by 7 kernels. Okay. And when we do so, when we are taking a dot product, we are also taking account the neighborhood pixels. Here we are in the highlighted part. There is 220211120. The updated pixel will be the one in the center, the one. Okay. But when we are updating it, we are also considering the eight neighboring pixels when we are updating our result. Okay. So doing this, we can take in account what the neighborhood of that pixel is, which type of which, what is the value of pixels around the pixel I'm currently considering. And this really gives us a very good edge, a very good answer to and a result. We extract more data than just looking at the image or doing just simple arithmetic. We are observing the relationship between the neighborhood of the pixels. Okay, so let's continue the video. And you can see this motion which is happening. It's just sliding through it. Will slide through the image. Yeah, Akash, just like in CNN, though it is a bit basic, but yeah, CNN is the more advanced version. So let's go forward. This is what the video is. And this is the representation of what is happening. Let's say we stop the time at some time frame. And here we can see that there is this 3 by 3 matrix H, which is going to do a dot product with our input image. It will calculate the dot product and update a pixel. Which pixel is updated? The pixel at the center of that input image. So when we were doing the dot product, the center of the kernel was at third row, third column. So the updated pixel will be also at the third row, third column of the output image. And using this, we established relationships and different stuffs between the neighboring pixels. So let's move forward. Okay, so one of the first filters we will use is known as blur filters or blur operation. Now, when you think about it, a lot of you might relate blur to smudging. The image doesn't look that well. But in the image processing domain, blurring is often referred to as smoothening the image. If your image is too sharp or has bad camera quality and noises, so in those cases, we need to smoothen the image. So there are three types of blur. There is mean blur, median blur, and Gaussian blur. So let's see each one of them. Okay, so mean blur. Mean blur, basically our kernel has a value of 1 throughout. And then we normalize it by dividing it with the total number of values. So if you are taking a 3 by 3 kernel, so you would have the kernel filled with 1, and then you will divide all the values by 9. In the second image, there's a 5 by 5 kernel. So all the values are 1, and then we multiply it by 1 by 25, so that each of them is having equal weightage. Each part of the kernel represent 1/9 of the output. So what happens is when I'm focusing on the image, I'm just not considering its individuality, rather giving equal preference to the all nearby pixels. This gives us a blur effect. Then in the third image, we can see we had an input image with flowers and background. In the background, the flowers are still identifiable. And if I were to work on it, it might be possible that I might also be my algorithm might be confused by the background photos. So I need to smoothen it a bit. So what I'll do is I applied a blurred filter, a box filter or mean blur. And what happens is though my original two flowers also got a bit smooth, but the background is now doesn't have that sharpness anymore. And I can easily work with it. Another type of blur filter is known as median blur. So what median basically means is that the central value. If you have a set of 10 numbers, arrange them in ascending or descending order and take the middle value. So here we can see that I have an image with lot of noises in it, white spots and dark spots. So if I were to work with it, my algorithm is definitely not going to work that well because the image is not clear. There is this white specks everywhere. So when I will take a median blur of it, when I will take a kernel, extract the values and take median of it, what will happen is since white and black are at the two extremities of all possible values, 0 and 255, we will always take the value of middle. So this white spot gets removed and we get this clearer picture. Though now we have lost a bit of facial expression and beard details, but we have a clearer picture and we can work with it. Moving further, the third type of filter we'll discuss is known as Gaussian blur. Now, Gaussian blur gives, you can think of it as it is giving the same output as mean blur. So why do we have this? Gaussian blur works pretty well because here you can see the central pixel has a value of 4 by 16. The immediately next pixels, which is up, down, left, bottom, is having a value of 2 by 16. And the farthest pixels, the diagonally away pixels, have a value of 1 by 16. So when we take blurring, when we apply filtering from this kernel to our image, what happens is we are not giving all the pixels equal weightage. We know that the central pixel have a relationship with the neighboring pixels, but we want the central pixel to also maintain its individuality. So what happens is the central pixel gets smoothened because there is a little bit input from the neighbors, but that doesn't destroy the identity of the central pixel. Now you might think, why Gaussian blur? We understood mean is taking a mean, median is taking a median. So why is this filter known as Gaussian blur? This is because it is based on this function known as Gaussian function. The function is not of our concern. It's something we don't care about. The curves are what you should see. The 3D curve, we can see that there is this maxima at 0, comma 0. And as you get away from the maxima, slowly, smoothly, the value decreases. When we convert it into 2D, we can see at 0, there is this peak. And after that, either direction you move, you would have a value decrease. And if you go back to our Gaussian kernel, once again, right? So if you go back to our Gaussian kernel, we can see that the center is poking out. It's very high in value, whereas the immediately closest to it are having a middle value, and the farthest away are having lesser value. So using this, we have a smooth blurring effect, and we can work with it pretty well. So moving further, I have a question for you. Why is mean blur not so effective? We studied three types of blur. Why do we require three different types of blur? I can just mean blur, right? So what are the cons of mean blur? There is a link, Slido link provided to you in the chat. Go through it and answer the question. Yeah, so there is the link right now. So we have a bit of questions. But if the image is more sharp, then the image has more details, right? So basically, we just don't want sharp image. We have an object in the image from which we want to work on. So though data should not be lost, data is really important. But in certain cases, it's a good compromise because by losing some data, I am getting a better quality data. So rather be with a good smaller data but a good quality data rather than just having a messy data from which I can't get a real conclusive result. Okay. Dot product basically is the physics dot product which we did, the dot product and cross product. We are just multiplying two matrices and getting a scalar value. Nothing new. All right, guys, answer this question. It's really simple. Just think what you think of. We'll discuss on it. All right. So let's see what you have attempted. So a lot of you have said 83% of you said that it gives equal weightage to all fixed. Uh, it is not that good, and 54% of you said that weightage is not decided by disease. Both. So let's see the answer. Yeah, so none of you did none of this option. And yes, mean blur has both of this problem. Since it is destroying the individuality of the single pixel, though I'm updating that central pixel, doesn't mean I definitely don't require its value. Its value needs to be at a higher priority, then the closest one, and then the farthest one. That's how we should blur an image. So let's go back to the slide. Very good answer. Okay, yeah, as discussed that let's say the Gaussian blur. Gaussian blur does the same. a better way because it gives the central pixel more weightage, and the weightage is also decided by the distance of proximity with the central pixel. Okay, let's go further and discuss another type of filtering, edge detection. Okay, so let's go back to the example where I was saying there is a black background and there is a bottle, and we are taking pixel and checking its surrounding. Let's say you check a pixel at the edge of the bottle, so the right side edge of the bottle. So to the left of it, of that pixel, let's say the pixel's value is 60, so the left pixel might also be 60. But to the right, the value can abruptly be 2 because the right pixel is no longer part of your object, but part of your background, part of another object. So from this example, we can understand that when objects change, when we cross an edge, there is abrupt changes. And this abrupt changes gives us an opportunity to identify objects, to find the boundaries of objects, to determine the edges. And it is very useful. Think about it. Let's say you are having an object avoidance drone or obstacle avoidance bot. When you are trying to avoid something, you need to know the boundary of the object you are trying to avoid. Just seeing an object doesn't necessarily mean that you can avoid it. You need to go beyond its boundary. So edge detection is really useful tool. And let's check out the kernels, different type of filters which are used for edge detection. There are a lot of those filters, but we will discuss just the two of them, which is Privet and Sobel. Sobel is basically just like Privet, but you can see, as in case of Gaussian, the up, down, left, right of the kernel are given a bit more priority than the farthest ones. But let's see Privet. So the two kernels of Privet, one of them detects the horizontal edges and one of them detects the vertical edges. So let's see the first one. Let's say there is this plane surface. All the pixels are having a value of 25. So what will be the output of Privet kernel if it does a convolution, if it does a filtering on that 25 valued surface? The top layer will give minus 25, minus 25, minus 25. The bottom middle layer will give nothing since it's 0. The bottom layer will give you 25, 25, 25. So basically, the dot product is minus 75 plus 0 plus 75. That means 0. Since there was no abrupt change, Privet kernel gave nothing. It didn't detect anything. On the other hand, let's say the upper part, you are at the edge of an object and the upper part is 25 and the lower part is 50. What would happen is the Privet kernel will give you minus 25, minus 25, minus 25, 0, 0, 0, and then it will start giving you 50, 50, 50. So final dot product is not going to be 0 anymore. It is not going to resemble black. Rather, it will be 150 minus 75. That's 75. It will give you a value. It will no longer be dark. It will go towards the 255 side. Greater the difference between the two edges, greater the value will be, and more that edge would get highlighted in our result. How do I mean that it gets highlighted? So let's see the output when you apply Privet, Sobel, or lot of different filters to an image. So here we have an input image. A man is looking through a camera with a tripod, and in background we have a lot of stuff. Since Sobel, we can see Sobel identifying the boundaries of the man and the camera. Sobel focuses on a bit foreground and gives us immediate edges. And we can see Privet not only identified the closer edges, but in the background as well. And then there are Roberts, Laplacian, and Canning. These different types of same kernels. They also have a kernel, and they gives us this abrupt changes and measure these abrupt changes and give us these edges. And this edge detection is highly useful. Let's say there is a satellite, and satellite needs to identify buildings so that it can find roads to go through in, for, let's say, Google Maps or any other app. So they use this edge detection to find boundaries of objects, even in fingerprints. Fingerprints also have these lines which you need to find and identify and relate it with the person. So edge detection is used there as well. It is a really useful technique. So going further, right. So now that we have seen filtering, this was a bit newer concept. So let's play with images again, and I would like to call Ayush again to show you how uh, how we can explore these images.
Yeah, thank you, Nikhil. So now
Yeah,
we'll be moving on to the practical section of the practical demonstration. So now first we'll be covering the rotations. So basically there are transformations as well where we need rotation of the image. So yeah, so here we get a 90-degree rotated image for. Okay, I think some people are waiting in the lobby, I guess. Can
sorry. Yeah, yeah, it's okay.
Yeah.
You can continue, Ayush.
Yeah. So once it is rotated 90-degree clockwise, this is the image that we get. Now we can also want to rotate it 90-degree counterclockwise. So this is the image that we get. If we want to rotate it 180-degree clockwise, so we have this function and we get such an image. It's like it's upside down kind of. When we want to flip the images, let's say around x-axis, we want to flip the image across x-axis. So we keep here the parameter as 0 in this function and we get this flipped upside down image. Now if we want flipped left right image, basically the around this y-axis, we want to flip it around this y-axis. So basically initially this red part here, it was on this side and this part was this side or on this side. So we keep this parameter as 1 and we get this flipped left right image. Now if we want to get an image with it, which is flipped both around both axes, the y-axis as well as the x-axis. So we use this parameter -1 and we get this flipped left right and upside down. So now let's see what different operations with respect to kernels are. So first of all, we'll be seeing the blur operations. We have this mean blur, we have this median blur, we have this Gaussian blur. So this is the result of different kinds of blurring. Excuse me. So the original image is this. When we apply the mean blur, the blurring is this kind of. When the median blur is applied, the blurring is quite different from what it was in mean blur. And when Gaussian blur is applied, this blurring, it's somewhat like mean blur, but this kind of blurring seems more nicer than the direct mean blur. Also, I would like to suggest all of you to maybe change one or two values here. For example, I'm changing here to 55 and see what I got. Even more melted kind of image. So you can experiment with these values over here. The 35, 35, this kernel size, or this as well. Now let's move on to the filters for the edge detection filters. So this is the image that we'll be using in the grayscale format. So if you had not run it, then run it once. Now we want the vertical edges. So we'll be applying the Sobel filter. You saw the Sobel filter in the theory slides. So when we apply only the Sobel filter only for the vertical edges, so this is what we get. For example, here this is a vertical edge. So this edge will be detected in the vertical when we want to detect vertical edges, but the eyes are not so visible. Eyes, the lips, those are mostly horizontal edges, these eyes and these lips. So we cannot see them very clearly. Now we want it to detect the horizontal edges. This time the lips are clear, the eyes are clear, but this vertical edge here, this vertical edge, it was detected here, but it is not detected here. So now what we want is we want the detection to have both the horizontal as well as vertical edges. So simply using this technique, we add the different pixel values for all the pixels. We simply by adding the two resulting images. So this is the result for it. Now, although it has detected every single edge present in both the images, but now the image has become kind of blurry or fuzzy, or maybe it has more objects than we want to detect. Let's say we only wanted to detect this human. So if we want to detect only the human form with hair and all, so we mostly use the Canny filter. Now this is the Canny filter that we use. Now if you like kind of look into this image, it is mostly showing only the kind of important features of the human. So uh, so this Canny filter, this is mostly used for human detection rather than and this one is mostly used for inanimate objects. So yeah, so that covers the all the image kernels and filters. So yeah, so now Nikhil will take over from here again. Yes, Nikhil, over to you.
Yeah, thank you, Ayush. So I hope you got a bit of interest after seeing those filters in action. So far, again, in the arithmetics, we dealt on pixel level. When we were doing work with image filtering, we tried to include the neighboring pixels as well and did a lot of options. But still, so far in this entire presentation, I have been talking about objects, objects, objects. But we never considered pixels as objects. We never considered them as a group of objects, a group of pixels as an object. Okay, so so let's start with this. And when we deal with pixels and assuming them as objects, we call those operations as morphological processes. And these are subset of image processing where we try to find out the shape or work with shapes and refine them. All right. So there are a lot of morphological processes which are used a lot. We'll be discussing a few of them. Okay. And let's start with the first one, dilation. Okay. So dilation basically is used when if you have an image and it has lot of finer details, let's say the image when we saw when we were talking about negatives, right? You can go back and look at it if you get time. That there were thin nerves, so it is very hard to observe them and to look at them for long. So what we do is we dilate an image. We dilate binary images or even colored images and try to look at those finer details. How do we dilate an image is basically we take a pixel and check its surrounding. If any of its surrounding is having a white color, in binary we call it 1, but if it is having a value of 255 near it, then we say, okay, the pixel I have selected is also a white pixel. What will happen is you can see in our example images there is this thin horizontal line. Let's say it is 2 pixels thick. So when I dilate it, I would be checking the line of pixels below it, and whenever I check I will find, okay, it is near a white colored pixel, so this is white. And that 2 pixel thick line will become 4 pixel thick line as there is a big line below it, and the line above it will also become white. And you can see in the output we can clearly see that line. The original image had small circles in the top left and bottom right, which you might have missed. There are small dots, thin lines, a lot of different circles, which we can miss if we just look at them casually. And using dilation, we can observe them really nicely and take observations and do our project. Moving further, the opposite of dilation is erosion. When I showed you the original image, I saw a lot of different components scattered, but I didn't get an idea of what I'm trying to present here. So in those cases, when we want broad view, we use erosion, which works basically the same as dilation. But when we take a pixel, we check if any of its neighboring pixel is having black near it. And if it is, then we also we tell the selected pixel is black. So taking the same example, that thin horizontal line, if I select a white pixel on it and check its surrounding, I'll say, okay, below it there is a black pixel. So this is also black. And doing this, that line completely vanishes. All the small dot vanishes, that thin circle vanishes, the diagonal circles at the corners, the top left and bottom right also vanish. All these smaller details vanish. And now I can see that the image basically has three concentric rectangles, two circle inside, a circle outside, a line above, and a knuckle-shaped object to the right. Right, and this gives me a good idea about how what the image tried to present. And this, though it seems like small dilation and erosion, they are basically used everywhere and not uniformly. Like you don't use dilation and start the product. project. You do dilation, then do erosion, then do dilation, and this gives a lot of different outputs. Let's say we do dilation and then erosion, okay, so that we take care of uneven surfaces. We do erosion first and dilation when you have a surface with holes inside it, so that when you do dilation, that holes get filled, and then you do erosion and you get a proper surface for it. Uh, Moving further, these were the morphological processes, and Ayush would show them to you in greater detail, and I hope you enjoyed. So over to you, Ayush.
Yes, thank you, Nikhil. Yeah, so first of all, we'll be seeing the erosion process. So first of all, we'll be having loading that image. So once this image is loaded, yeah, the image is loaded. Now we'll be running the this piece of code, and it will result in this image is the eroded image. So the white has become thinner, and here the white has become thicker. So basically, this is mostly used in number detection or maybe letter detection, where you have to where you have something like where if you have got a very fine one, you want that one to be more visible to your system, to your computer, then you will be dilating that one. Similarly, if you have something when the one is let's say very thick, and you want it is not kind of very visible to your computer, to your system when you are running the code, so you will erode it. So that is what basically erosion and dilation is. Also, you can change the path here, maybe let's say colored path, the Rubik's cube image, and you can check that out as well. So so yeah, all the black lines here, they have become thicker, and the black lines here, they have become thinner in relative to the original image. So you can test with different kernel sizes what happens. The kernel sizes you can change with this. So yeah. Okay, so that covers the complete morphological processes part. Now I would request Ananya to come and take the session further.
Yeah, thank you, Ayush. So, we studied a lot of image processing functions today, haven't we? Like, I think Tanushree, Ayush, and Nikhil have done a pretty good job in explaining those. So, now we are going to look at some real life examples in which computer vision is actually used. So, can we go on with the slide? Yeah, so our first example is going to be air hockey table. I think I think most of you must be familiar with what air hockey is. It's a pretty famous game you can find in every game zone. So yeah, in this we are going to see an air hockey table along with the camera setup. So what the camera setup does, it actually detects the path using image processing functions, and using those paths we predict a future path, and that helps the goalkeeper to save the puck from scoring a goal. Let's see the video. Yeah, so that was a pretty awesome video. Now we are going to see another video which is related to obstacle detection, which is also a major uh, field in which computer vision is used. So we are going to see an autonomous drone that is built for flying to fly avoiding any obstacles. Like you will be seeing in this video that the drone is going to fly avoiding any trees or anything that is coming into his path, and it's going to fly autonomously. I think there's a connectivity issue. Just give us a couple of minutes. Yep, we are back. Yeah, Ayush, I think we are clear with the video with this autonomous. Yeah, so that was also a pretty cool example of where computer vision is used. Moving on. Yeah, so the last part of today's session would be the winter workshop. So I'm really excited to announce you to guys that we'll be conducting the Winter School of Robotics and AI 2022 soon. So, what are we gonna teach? What is this winter school all about? So, it is basically a workshop. In this workshop, we aim to introduce the students to concepts of different verticals, and we are going to have three verticals this year: computer vision, which was a little introduced in today's session; autonomous robotics, which was introduced in Craig 201; and machine learning. And while computer vision and autonomous robotics are open to both freshers and sophomores, machine learning is exclusively open for sophomores only, and it's free of cost everyone. So it's open for all. So make sure you participate in that. So what used to happen was this workshop was used to be conducted in December after the completion of autumn semesters. Like everyone used to have their vacations. So at that time, winter school used to happen. But due to the pandemic and since the academic schedule of first year students have shifted, we plan to organize the winter school this year in the month of March. So the workshop would span over 3 weeks in the month of March, and we'll be conducting the classes over the weekends. There will be mentors assigned to all the mentees, and the classes will be conducted over the weekends to ensure that the students get sufficient time to complete their assigned tasks, and it's not hectic for anyone, be it mentors or the mentees. Yeah, so these workshops are aimed to have a hands-on session. So teaching will be followed by tasks and problem statements in the respective verticals. So for having to make models or tackle these problem statements, certain components might be required. For example, Arduino or some kind of sensors might be required for some autonomous robotics problem statement. So we provide you these components with the freshers kit, which was already introduced to you guys in our Craig 201 session. So it's really beneficial for your understanding to have a good hands-on session, to have a real life example or problem to do. It certainly helps you to absorb the concepts better. So I definitely recommend you guys to take like check the freshers kit out if you haven't already. You can find more information about in our on our official Facebook page, official Technology Robotics Society Facebook page. Yeah, and for winter school, you can check our website winterschoolai.robotics.in. All the information regarding the timeline, the freshers kit, everything is available over there. So make sure you check the website out. Another thing is that we don't require any prerequisites as such for this winter school. All the things will be taught to you from scratch only. No coding exposure, nothing is required. All the any programming language or associated library, if needed, will be taught to you guys from scratch only. So you don't need to worry about any prerequisites. So yeah, we have now reached to the end of this session. We hope you got to learn something new today from us. And for further such sessions, make sure you keep an eye on our Facebook page. All updates regarding related to Technology Robotics Society are posted on our official Facebook handle. So make sure you keep an eye on that. Yeah, and it was really nice having you all here in this session. If you have any queries regarding today's session or the upcoming winter school, please write it down in the chat box. We'll be answering them.
But during the winter school, we will having mid-sems from 14th to 21st March.
Yeah, so we'll make sure that it will be conducted after your mid end sems. Yeah, like after your first semester, we will keep that.
Okay, and one thing I would like to ask out of this topic means, are these do TRS help students when students go in offline mode?
As in offline mode.
Means when we will be going to the campus, means students not present in TRS, are they being helped in any way to proceed in the field of robotics?
Yeah,
Again,
sure.
these workshops are for everyone. Sorry, Nikhil, I
Yeah,
interrupted
sure.
you.
And
I'll
then you
just
can.
take this question. So, these workshops are for everyone. And what used to happen in the offline semesters was when things were offline, uh, everyone used to come and like attend these sessions and all the hands-on sessions that we had in the last K.R.A.I.G session. After K.R.A.I.G 201, we had a hands-on live hands-on session. So those were done in the offline mode for everyone. It's not just for the members of TRS. It's open to all. So yeah, I hope it answers your questions.
All right. Does anybody else have any doubts? So they can write in chat or speak up. Anything related to topics covered, anything related to winter school.
Hello, can the freshers get pre-ordered anymore?
Yes, it can be ordered right now. You can order it.
In the end of winter school, is there some competition? I mean, I was just checking the website. After all the lectures, you are releasing problem statements. So, what is that? What is that about?
So basically, we would be discussing on it a bit more when winter school starts. But after you learn, we will be working on a project, right? And it's how it, to show how, what we have learned and practical experience. Like we did the hands-on session in the K.R.A.I.G 201 after it. So like what you learn, you implement it as well. It's a part of that. It will be discussed more, and finer details will be told when the winter workshop starts. It's nothing to worry about now. Ellen, registration of winter school will be started soon, and it will be intimated by our Facebook page. Yeah, yeah, that's it.
And will there be a Craig 401?
No, I think that this is so. There will be a lot of seminars more which we are planning. Stay tuned for our Facebook page. We will be telling that to K.R.A.I.G, and there are different seminars, hands-on sessions, hackathons which have been planned. And once we will be posting them on our Facebook page. So are there any other doubts regarding anything discussed? So if we don't have anything, so we can end this meet. So all right. So it was fun teaching you all and discussing stuff with you. Have a great day. You can leave the meeting. We'll be ending the meet now.
Hello. Sir. Hello.
Yes.
Is somebody speaking?